Hello everybody and welcome to our third day of EuroPython. We hope you have enjoyed your evenings. If you attended a code jam, we know that was an Italian man who was born this year, finally. So, it was quite a lot of years, so people from all around Europe did win, so it was a bit of Italian pride in the last year of EuroPython. Let's welcome Giles, I'm sorry, and his talk on what he has learned on serving a very lot of Python consoles with Tornado. Thank you.
That's a good start, isn't it? Okay, can you hear me now? Good. Yeah, so excellent turnout. Thanks a lot for coming. It's 9 o'clock in the morning and there's a lot more people than I was expecting. This is good, but there's one potential risk. The thing is, normally I speak very, very quickly. I'm talking to a lot of people, so I'm going to get nervous and then I'm going to speak faster and faster and faster. So what I want to start with, just saying for everyone, if I start gabbling and you can't understand a word I'm saying, hold your hands up like that. Let's have a demo now. Imagine I'm speaking really quickly. Hold your hands up like that to tell me to stop. Great. Okay, now I know what to look out for.
You're already speaking.
There we go. Excellent, excellent. The protocol works. A bit further up. Okay. Any better? No. Maybe. I'll try and speak very slowly anyway. Okay, so I'm Giles. I'm from Python Anywhere. How many people here have heard of Python Anywhere? Okay, quite a few people. So for those of you who don't know, Python Anywhere is a company that specializes largely in doing ridiculous lightning talks where my colleague Harry here tries to get everyone to rap with him. But what not so many people know is that we actually have a website. And that website is basically an online development environment for Python. You can host your own Python code there. You can do web apps. You can build long-running applications that query stuff on the internet. The interesting thing I want to talk about today and how we built it is this. This is basically a Python console, but as you can see, it's running in Chrome. The title of this talk is how we served what we learned from serving 250,000 of these consoles out over the internet. You can see from the console ID at the top there, this is ID 270,000. So we've done 20,000 since I actually wrote the title of the talk. These consoles are basically, the front end is running there in JavaScript inside a web browser. It's talking to a Python process which is running on a back-end server somewhere out on Amazon Web Services. And we use Tornado to be able to interface between the in-browser JavaScript console and the process that's running on the back-end server. So what I want to show you today is basically how that code works. I'm not going to show you. Sorry, here's a pretty diagram just showing exactly how that works, right? So we've got our front-end browser, we've got Tornado, we've got a Python process at the back. I'm not going to tell you anything about how the JavaScript works because this is PyCon, it's not JavaScriptCon. I'm going to focus entirely on what's happening inside Tornado. Why do I want to talk about this? Well, what we've managed to achieve with this Tornado server is something that can provide inside a browser basically the same kind of latency, the same kind of capabilities as you'd get from SSHing directly into a server, which I think is actually pretty cool. So we've used lots of interesting technologies in that, lots of interesting tricks. We've also made a bunch of really bad decisions along the way. This is because we're a very agile company. We believe in doing everything really badly, really quickly, and then fixing it later when it turns out to be important. We don't deliberately do it badly. The important thing is that when we started Python Anyway, we had about 300 ideas of different things we wanted to put into it. We thought we'll have in-browser consoles, we'll have web applications, we'll have this, we'll have that, we'll have the kitchen sink. We didn't know which things people were going to use. What we wanted to do was get something together quickly, put it out there, and see what people liked, see what they're actually using. And then later on we'd know, then we could go back and do the research and improve things and make it proper professional quality. The consoles were 270,000 served. They're a very popular part of our application, so we put a lot of work into that. Other bits, maybe the code's still a little bit creaky because nobody uses it. Maybe we even pulled those bits of the software because nobody was using them. So some people here might already know exactly how you do something like that. Maybe there's somebody in the audience right now thinking, well, you know, it's pretty easy, right? All you need to do is run some kind of BT100 emulator inside a browser, use WebSockets or something to send it back to the server on Tornado. Yeah, I don't know, probably use a pseudo terminal just to fork off a quick Python processor to communicate with, and then use epoll to listen for changes on the file descriptors from the back-end process and send it back up to the front end, back over the WebSockets connection. Did anybody in this room actually understand everything that I just said in that sentence? Okay, a few. I'm very, very glad to see my colleague Harry held up his hand there, and Hansel as well. Okay, good, good. Hopefully by the end of this talk you'll understand everything in that. I'll try and say the same sentence or a close approximation to that sentence at the end, and hopefully everyone will understand it then. But anyway, yeah, that is what we do. Quick terminology check just to make sure that we're all starting from roughly the same level. Who here understands pretty comfortably what WebSockets are? I'm scanning around. There are a couple without their hands up, so I'll say it fairly quickly. Or rather, I won't say it very quickly, I'll say it fairly concisely. So, traditionally, the way that you'd interact with your server from a browser is that you'd make HTTP requests. And that's a very simple protocol. You make a request, you get a response coming back. The problem is if you want to push updates from a server, it's actually quite hard. There are various hacks that people have implemented on top of HTTP to make that possible. And you know, they can sort of kind of work, but it does get very difficult if what you really want is a persistent channel between the client and the server, and you want to be sending data backwards and forwards on a kind of ad hoc basis between the client and the server. Obviously, being able to do stuff like that is really important if what you're doing is running a browser inside a console, talking to a back-end process on a server. But it's also useful for things like, you know, as simple as in Facebook, when somebody likes your picture of a cat in a bathtub, then the little thing lights up in Facebook to say that you've received a like. So WebSockets were implemented basically as a way of achieving a persistent connection between a client and a server using a basic web standard protocol. Okay, asynchronous programming, hot topic. Who knows what I mean by asynchronous programming? That's actually a trick question because almost everyone means something slightly different by asynchronous programming. So the way I'm going to use it is basically when talking mostly about what's often called non-blocking I/O. So traditionally, when you want to, let's say you've got some code and you want to access, you want to download the index page of google.com. So you use requests.get http www.google.com. Your code blocks, it sits there, it waits until the response comes back from Google's notoriously slow servers, and then your code continues executing. Okay, so you've got your data, but your code just paused and did nothing for a while. With the asynchronous model, with non-blocking I/O, what you do is you call your get function, and you pass in a URL, and you pass in a callback function, and your code then carries on executing, doing whatever you want it to do, and when the data is available, the callback gets called. Now that's quite a nice model. It allows you to use more of the CPU, it allows you to do much more processing. But it does become relatively complicated. I mean, that was a simple example, but imagine if you've got hundreds of these callbacks to deal with. It can become a bit of a nightmare dealing with them all. There are clever things like gevent that allow you to do non-blocking style I/O in a blocking style, but I'm not going to go into those because we don't use them. Last terminology check. PTY, also known as a pseudo terminal. Who knows what a pseudo terminal is, or a PTY? Who has seen PTYs on their Linux desktop, on their Linux machine, and thought, that's interesting, I should work out what those are someday? Now I'm worried because Harry is holding his hand up.
I still don't get that, really.
Good. Excellent. Well, in that case, I'm going to explain it. So, actually, even in researching this talk, I think I learned more about what this is all for. So, okay, so when you run a process on a Linux workstation, on a Linux machine, then it's got to know, am I running as an interactive process, or am I doing some kind of batch processing? Let's think about Python, for example. If you start up Python normally, just with Python on the command line, it gives you an interpreter. If you start up Python and pipe in a file, then it actually executes that file. Those are two totally different execution modes when you think about it, because in interactive mode, you type in a command, it responds straight away. if you're processing a whole file, then it reads the whole file in, and then only then does it start executing it line by line. That's actually pretty different. What is the difference there? Well, Python knows when it starts up, am I talking to a terminal? And when I say am I talking to a terminal, what Python thinks is it's talking to one of these guys. That's a DEC VT100. So what's interesting is that these days when you start up Python, it's very rarely talking to one of those. In fact, I haven't seen one of those since 1994, and that was with a very, very determinedly old-fashioned colleague of mine. Normally what's happening is Python's talking to Xterm, or it's talking to an SSH client or something like that. What actually has happened underneath the hood inside Linux is that the operating system has to fool Python into thinking it's talking to one of these. It has to fool it into thinking that it's talking to a terminal. So it creates a thing called a pseudo-terminal, a PTY, which is particularly wonderful because the TY comes from teletype, so we're really talking old school stuff here. So PTY is basically an operating system trick to persuade a process that it's really talking to one of these, whereas in fact it's talking to another program running in the same system. You can probably see why that's kind of useful in something like we're talking about here. Okay, enough background. So when I was preparing this talk, I had a lot of fun digging around in our Git repository, and I found the first version of the Python Anywhere console server, and it was amazing. It fits on a slide. Unfortunately, it's that slide. So, okay, you probably can't read any of that. I'm going to delve into the code bit by bit. Here's a nice little structural diagram of it. Absolutely beautiful. You can tell that I'm the artistic guy in the company. The blue box there represents Tornado. We've got the browsers at the top. We've got the Python processors at the bottom. So that is a Tornado server that's serving up 2 Python consoles in this very simple version. We have a process connection class, a process connection object for each one of the connected browsers, and that handles all of the communications over WebSockets. And then we have a process wrapper class, which does all the handling of pseudo terminals to talk to the Python process. Let's take a look at the code. So focusing in here on the process connection. So I said we're using WebSockets. That's almost true. Not every browser supports WebSockets. And so sometimes it can be useful to be able to support the more traditional hacks on top of HTTP to get this kind of communication between your browsers and your servers. So there are lots of libraries that wrap this up for you. One of them is called Socket.io. This is the one we started with. We don't use it now, but Socket.io is worth a look. Sock.js is the one we use now. It's better for reasons I'll explain later. Socket.io basically presents to your JavaScript end something that looks very much like WebSockets. But under the hood it uses WebSockets if they're available. Otherwise it just fails back to using the various HTTP-based hacks to achieve the same kind of goals. So going from the bottom up of the code here, you see we've got a main routine which basically says create something that every time a WebSocket connection comes in, we create one of those process connection objects, and then that will handle that particular connection. So we have one process connection object per WebSockets or Socket.io connection. The process connection itself is really quite simple. It's got an onOpen function, an onOpen method rather, which when it's called is going to fire off one of those process wrappers. So we've created our object structure, and it's passing into the process wrapper self.send. The send method is inherited from socket connection, and what it does is send something to the browser. So now we've got a process wrapper that has the ability to send data up to the browser. That handles one direction. That handles the way in which we can send stuff from the process to the browser. What about when the user hits a key? Well, that's when the onMessage function is called. OnMessage is basically, I have received a message from the browser. What should I do with it? So again, here we're passing it through to the process wrapper. When we started writing this console server, we knew we needed to use a PTY or equivalent. We knew we needed to force Python into a interactive mode. The PTY module in Python looked a little bit scary. And in the interest of doing stuff quickly, then we decided, well, we won't use PTY initially, we'll just hack something in. In fact, we knew that there was this brilliant library called pexpect. Pexpect is designed for automating tasks using, basically turning interactive programs into non-interactive programs so that you can so that you can do batch processing with them. It's based on a Perl module called expect, and they called it p-expect, so that you could distinguish between Python expect and Perl expect. However, in order to do that stuff, it does basically create pseudo terminals for you. So we use that. The problem with p-expect is that the way you read from process is using blocking I/O. This is a bit of a pain, because if you're using blocking I/O, that means you've got to have something that sits there and listens to that process. And what that means is that in our code we had to start using threads. Now, people when presented with a programming problem, etc., etc., etc. We had to create one thread per process wrapper, and that thread had to sit there and block and wait for from output from the process, the Python process that it was manipulating. So, I don't know if you can read the code particularly well there, but at the top here, I'm creating a thread, passing in this read process output thing as the function to run inside the thread, and then inside there we've got a while true loop, read stuff from the process, and then call an on output function, which basically goes all the way back to the function that sends it back over WebSockets to the client. This is ugly code. This is really ugly code. In particular, what's unpleasant about it is that we've got this read non-blocking thing here. Read non-blocking. Any sane person would think that a function called read non-blocking would be doing non-blocking I/O, but it blocks. And it has two parameters passed in here. Size, where we're reading 1 byte at a time. We've got a timeout of 60 seconds. We go through all kinds of convolutions to get that to work. And I notice I've got 14 minutes left, so I'm going to have to go through some of these slides a bit more quickly. Okay, don't use this code. We've got threads doing blocking reads. There's no authentication. This stuff was pre our private beta. I don't think we even ever ran it on the public internet. It's a mess. I'm going to move fairly quickly over some of the things we put in there. But first, it was built in one afternoon. In 4 hours, we've gone from a system where you could just start a console inside a web browser, and you could see the Python console. You could interact with the console. It all just works. Okay. We added authentication. I'm not going to go through the details of this because it's not particularly exciting. You add authentication to web apps. We added Unicode support. Unicode support was really easy. No, it wasn't. Actually, Unicode support, here is a sample of the check-ins. What's exciting about these are the very first one says, hey, Unicode just works. The last one there, when Unicode really did work, was 4 months later. Take that, Unicode, is in the second from bottom one there. I think we were getting quite frustrated by then. We added multiple sessions, so you could have multiple connections into the same console. This is a fairly bog standard model view controller kind of pattern, isn't it? So I mean, each process wrapper talks to one process, and we have multiple connections, each one handling one connection for one browser. What's great with that is that means multiple people can connect to the same process, they can work in the same Python console. Also, that you can disconnect from a Python process and leave it running. So this was almost one of our first ideas about how we should, how Python should work. You should be able to start coding at lunchtime in the office, and then when you get back home, pick up from where you left off in the same console. Yeah, as I said, Socket.io is that wrapper we're using over WebSockets. Sock.js is better. It's faster. It doesn't have a particular bug. It doesn't use any Flash whatsoever, which is absolutely fantastic. So if you want to do something like what we're doing, then use Sock.js. Back to that horrible code. There we've got the number of bytes we're reading at a time and the timeout. We did a lot of tweaking of those two numbers, a hell of a lot of tweaking. I can show you a bunch of them. So we tried increasing the size up so that we were reading more data at once, because if you're reading 1 byte at a time, it's really inefficient when a process is outputting lots of data. So great, we tried reading a megabyte. And we lower the timeout down to try and improve the latency so that when you press a key, you get results back really quickly. Hey, guess what? If you send a megabyte of data down a WebSockets connection to Chrome, it crashes. Your users get very unhappy. Don't do that. Okay, so after a few angry emails, We lowered the size. We're doing 200 seconds. We've reduced the timeout still further because we're trying to get latency working, get the latency down. It's great. This one almost works, except it sucks up loads of CPU because that timeout's quite short. So we're going through that loop thousands of times, well, hundreds of times a second per connected console in our console server. It's not. Sorry, let me correct that. It's not per connected console, it's per process that we're actually talking to. So we've got a Python Anywhere console server that's been running on our cluster for a while. There have been maybe 1,000 consoles started. Some of them are still running. You've got 100 threads, all of which are doing 100 iterations a second through a loop like this. Your CPU load goes through the roof. So we fix that. We add what's called chillax mode. Thank you, Harry. In chillax mode, we detect whether somebody's connected to a particular console. If somebody's connected, then we do the 200 bytes at a time thing to give them really snappy, usable consoles. But if nobody's connected, we start chillaxing, and we read lots and lots of data, and we just stash it in a buffer so that when somebody reconnects to that console, they get all of their data coming back. Epicycles. Who knows about epicycles? Epicycles? No, this isn't a programming term, by the way. It's from astronomy. Yeah. Okay, so for those that don't, epicycles. People at one stage believed that the planets orbited the Earth, and the problem is that if the planets orbit the Earth, then what you expect to see is that in the sky they'll go across the sky like that, but they don't. They go across the sky in patterns like that. So they thought, okay, well, instead of rethinking their core assumption, the planets went around the Earth, they thought maybe the planets actually go around the Earth in these little circles of circles like this. And these circles of circles were called epicycles. Exactly. So the thing is, it's really easy to start adding epicycles. If you're more into artificial intelligence, we're talking about hill climbing here. The problem is you start off with a core idea which is wrong, and you keep tweaking it and adding extra bits of code. And the thing is, you're moving forward, you're making your system better. At every stage it's a better system. This chillax version of our console server was great. It lasted for about 6 months before it started developing problems of its own. But if we'd actually rethought our core idea near the start, then we would have wound up with a much, much better system. What actually made us discover we need to rewrite all of this was select. Select, okay. Another question, who knows select? Okay, select is a Unix system call. Basically, you give it a list of file descriptors, and it tells you whether there's activity on one of them. It has a couple of problems. Unix file descriptors are integers, and if you've got lots and lots of files open, then those integers can get quite large. If, for example, you've got a console server like we had with maybe 300 processes running underneath it, you're going to have a couple of file descriptors for each one of those processes. Great. The number's going to get very large. If you've had 1,024 of them, your number of file descriptors can get over 1,024. Guess what the limit on select is? As soon as the file descriptor number gets over 1,024, it explodes violently. We were ultimately using select as part of the pexpect read non-blocking call. Read non-blocking was using select under the hood to try and implement those timeouts that we were tweaking so much. And select was exploding because we had too many open files. This wasn't a problem when it meant that we had a crash every other week or something, but eventually it got to the stage where it's crashing almost once a day, and people were losing state and angry customers, angry emails. Not a good thing. So we thought, let's use something more modern. There's an improved version of select. It's called epoll. It's new, it's shiny. It doesn't explode when you give it high file descriptors. It's also slightly faster. Select, I think, is roughly in performance equivalent to order. It's linear with the number of file descriptors you give it. Epoll's faster, I think, log m, but don't quote me on that. So we thought, how can we use epoll? Well, the thing is, we're using pexpect, and how do we get a file descriptor out of pexpect? And then we thought, that's a silly idea. Let's stop using pexpect. Let's do what we should have done. Well, maybe not what we should have done, but what we know we should now be doing, and actually create our own pseudo terminals. So this is how you create a pseudo terminal in Python. It's not difficult. Use the PTY module. You call fork on it. What happens with fork, PTY fork, just like with a normal system fork, is your process carries on executing. It creates a new identical twin. Both of those identical twins then return from fork at the same time. The parent process gets the process ID of the child and a file descriptor for communicating with it. The child process gets 0 for the process ID, so it knows it's the child. So it then calls the operating system execve command just to replace its process image with the process image you want. So that's how we decided, let's start up a Python interpreter. Inside the child we start up Python. Inside the parent, what we need to do is start listening to that child and trying to find out what it's got to say to us. So we thought, okay, how do we use epoll to listen to those file descriptors? How do we detect when there's input on those things? Then we thought, you know, Tornado, it's one of those kind of asynchronous things that's meant to be pretty good at stuff like listening to file descriptors. Maybe it's got some kind of function for that. Well, yes, it does. In fact, it's one of its most important, the most important parts of its API, which we'd somehow missed until this point.
It was only about 2 years later.
Exactly. So in Tornado, if you just call ioloop.instance.addHandler, okay, it's a bit of a long line, but it works. You pass in a file descriptor and a function and a bit mask of the kind of events you're interested in. Then Tornado will call you back every time there's some kind of activity on that file descriptor. Suddenly, we've got something where we can get rid of those god-awful threads. We can get rid of pexpecs. We can get rid of the epicycles. We can create our new heliocentric universe based around asynchronous programming. And this is actually a slightly trimmed version of the real code we have right now to read the process output. So if we get a HUP from the client, that is, the Python process is exited, we close the console. We then try and read from it. If we get an error, we log that. Fine. We also close the console because it's probably broken. Otherwise, I'm not going to go into the details of this first byte thing. Come up and ask me later if you're wondering why there's that little extra bit of cruft there. Otherwise we just send the data straight out to the connections. So we've received data from our sub-process and we've sent it out to the connections. I probably do have time just very quickly to say we'd had a bug in our console server for a long time where it seemed to be queuing stuff up very, very rapidly. We didn't know why. Just as we were looking at the PTY fork code and thinking, yeah, we should just have a quick look at pexpect and see if there are any clever tricks we should be using with PTY fork to make sure that everything works smoothly. Hansel, I think, came across this particular line in pexpect. The reason we were getting all these random delays is because pexpect, because it's not designed for what we're using it for, it's designed for something totally different. Then it does a little sleep for a 20th of a second before every key it sends down to the sub-process. Oh, and it was doing that on the main Tornado loop, so that meant that all of the other processes got locked up for a 20th of a second as well. I'm not quite sure what to say about that apart from, oops. Apologies to any musicians there, because you'll be able to tap out that particular rhythm and then you've got a terrible earworm that will stay with you for the rest of the day. The code still fits on a slide. It's fantastic. This is our complete Tornado server as it stands. That's 1.text. It's still pretty short though for something that's doing what it's doing, because what it's doing is every time a client makes a connection over a WebSockets connection down to the Tornado server, then what we do is we fork off a new pseudo terminal to run Python in. We then use Tornado's built-in epoll support to be able to read data from that sub-process, and as the data comes back from the sub-process, we send it back over the WebSockets connection to the browser. And hopefully that time everybody understood what I was talking about. All right. That's it basically. I don't know how much time we have for questions, but please ask them, and if you don't have a chance, ask any of the people on this slide, and also ask them for a t-shirt.
Oh, we start from there.
Okay.
Hello, did you try to use Twisted instead of Tornado?
We looked at both Tornado and Twisted, and I know it's a bit of a cliche, but Twisted scared us a little bit. Tornado looked easier, and they seem pretty much equivalent in their capabilities for what we're doing.
Because in Twisted the same functionality you could write in asynchronous of code.
There's the code backup. Sorry, you mean on this particular code here? There's a lot of extra stuff in there which I didn't go over, like the authentication and stuff for handling killing consoles and things like that. So, yeah, the core of our system right now would probably be about the same size as that first slide I showed.
There was somebody from this side.
Hi. You mentioned that you solved the problem of too many open files just by moving to epoll and everything. But now you have... Oh, what? So sorry. Now you're forking every time a new connection comes in. Are you? Do you think you will run out of too many processes in your Unix system?
Yeah, that's certainly a possibility. Actually, we don't fork every time there's a new process coming in. There are two kinds of connections that we can handle. There's a new process, so somebody wants to start a new console, but you can also connect to a pre-existing one. So that's the case where you start working on something at lunchtime, and then you go home and you pick up from where you left off. So in that case, there's only one process running. But yes, yeah, you can get to a stage where there are too many processes, but in general, we believe that if somebody's asked for a process to be kept running, they want it to be kept running. And that's, we are billing people for that if they're using more than a certain amount of CPU, so that's a good thing. So obviously, we can't serve all of this from the same server. We have a number of console servers to handle the number of users we have.
Thank you. Any more questions?
I think there's one around there on the other side of the pillar from you.
I can't see it. Oh, from behind the column.
Thanks for the talk. Just a quick question. Do you know who's your target? Who is going to use this kind of Python console on the web?
It's an interesting range of people. For example, there are a lot of people who are just getting started with Python, and they're actually a little bit scared about installing Python, especially when you need to learn things which are second nature to any seasoned Python programmer, but like pip or easy install to install modules. So there are lots of beginners like that. There are also a lot of people inside companies where they can't install Python. I was actually talking the other day to a guy at a venture capital company who had to scan lots of, basically they want to keep their eye on an awful lot of startups, and so he needed to do lots and lots of web scraping stuff. But ironically, despite the fact it wasn't part of his job, it was part of his job, they wouldn't install Python on his workstation so he could actually do his job. So he signed up and got an account with Python anywhere so that he could actually do his job for that. Then there's just people who want to be able to do stuff at work, do something outside the boundaries of work from work, and then pick it up when they go home. I think
okay, like the actual answer to that question, right, is the target market for this is you guys. Like what this is a full browser-based Python programming environment that you can access from absolutely anywhere. From your own computer,
oh, no, here we go.
From a French computer, from a Thai internet cafe. Like you've got a whole real Unix environment, it's got a file system, it's got 1 million Python modules, you can install new ones. You've got free web hosting for little throwaway web apps. You can sign up for a free account and just have a thing on the web in about 30 seconds. So like it's totally awesome. Everyone should sign up, and Sunday everyone should pay us money for it as well. Thank you.
So now I think Harry should have been wearing the Toads Marketing Balls t-shirt. It is actually inspired by a quote of his anyway. He would have only tried to make everyone rap.
One more question.
So my one question is, what sort of isolation do you provide between different customers? You mentioned you have a console server, and how do you isolate those?
Right now, it's actually pretty basic. What we've got there is troots to make sure that people's file systems are separated, and everyone's running as very low privileged users. We're adding on extra bits to that. Basically, the nice thing about Linux containers is that it's built out of a number of different modules. So it uses roots for file system protection, it uses network namespaces for the network side, and so on. Process namespaces for isolating processes. The great thing about that is we don't actually want to be creating a full Linux container for every single console that somebody's creating, but what we can do is take different bits from Linux containers and kind of create our own custom virtualization with very little effort. So that's the direction we're going. One more at the back there.
Back there. Please pass the microphone, please.
Thank you. It was a great talk. I arrived a bit late, so I hope you didn't talk about it at the really beginning of the talk. I was just wondering, do you consider extending the basic console with like visualization, like a bit like IPython, this kind of thing, where you have the notebook, this kind of thing? I was just wondering because that would make it even more useful for your target audience. Stop.
Yeah. In fact, when we first started doing this, one of our dreams was, I don't know if you use the JavaScript consoles inside web browsers, but sometimes they can have some really cool features. Like if you print an object, it won't just print a string representation. That will actually be an unfoldable tree, so you can actually delve down and look inside the object. So we thought it'd be pretty cool to add that to a Python console as well. It's one of those things which we've always wanted to do, but it's never quite reached the top of our queue. There's always been other stuff that people have been asking for. Another way of achieving similar goals possibly would be to use, there are other good ways out there of doing that kind of console, like an IPython notebook. So we're thinking maybe we should just host IPython notebooks as well. That would require a little bit of work on our side, but much less, I think, than writing a super smart console.
More questions? Everybody satisfied? Okay, so thank you very much.
Thank you.